Welcome, ladies and gentlemen. May I have your attention, please? Thank you. And so as we work to apply the chain rule, we have to first identify the overall function versus the inner function. So please be ready to share with the class when I call on you. And number one, is the overall function a logarithmic function or a trigonometric function? What's my overall function here? Katie?
Logarithmic.
Logarithmic, I would agree. This is ln of cosine of p. And so my overall outer function is logarithmic. So I'll start out with my rules for differentiating a logarithmic function. That's just 1 over the function. In other words, the derivative of ln of x is just 1 over x. The thing is it wasn't ln of x, it was ln of cosine of p. So we have the opportunity to use the chain rule. Let's do it. The derivative of natural log is 1 over the function. My function here, though, like we just said, is not x, it's cosine of p. So that'll be my inner function, and then times the derivative of the inner function. So it's the derivative of the overall with the inner, and then times the derivative of the inner. The derivative of my inner cosine of p is opposite of sine of p. And so I put it all together, and it looks like I'll get a single fraction, negative sine of p over cosine of p. So we could probably write that as negative tangent of p to make it look nice. And again, if you already had that. So who already had negative tangent of p? Yes, you did. Good job. Let's take a look at number 2. And number 2, right, is my overall function logarithmic or power. So is my overall function logarithmic or power? Blake? Logarithmic. And so again, we could go ahead and do our chain rule, starting with the derivative of a logarithmic function is 1 over the function, and then times the derivative of the inner function, right? That would be the derivative of a power function. So we could do it that way. However, I want you to know that oftentimes rewriting algebraically can result in a simpler derivative rule, right? Or as we'll see next semester, a simpler integration rule. And so I want you to do this problem 2 different ways. First way, let's do the chain rule. So the derivative of a composition of functions is 1, right, over the function. There's my logarithmic derivative. And so the overall function goes to 1 over the function. And then times the derivative of the inner function. In this case, my inner function is t to the 4th. That's a power function, so I'll do the power words, right? The power rule for the derivative of the inner function, 4t cubed. And we'll put it all together. It looks as though we've got 4 t cubed over t to the 4th, and we'll reduce that and get 4 over t. I get 4 over t. So raise your hand if you got 4 over t. Anybody else get 4 over t? That's good news. Now I want to go ahead and consider the alternative. That is using logarithmic properties to rewrite first, and that will result in an easier differentiation. Recall the log of a power property, which allows me to bring down that exponent as a constant multiplier out front. So in a rewrite, not a differentiation, but a rewrite, this is the same as the derivative with respect to t of, let's bring down that exponent in front for ln t, right? That's the log of a power property. I can bring down that exponent as a constant multiplier in front. So this is the same problem. However, I no longer must use the chain rule because it's now it's not ln of t to the 4th, it's just ln of t. And the derivative of ln of t is the same as the derivative of ln x is 1 over x. The derivative of ln t is 1 over t. So this would be a simpler differentiation because now we just have that constant multiplier out front. It stays around for the party. What's the derivative of ln of t? 1 over t. And lo and behold, what do we get? Exactly the same thing, 4 over t. Which one is easier, the first or the second way? The second way, right? Shorter derivative rule, so it's easier. I mean, of course, you have to remember your log properties and do the rewrite. So maybe it's not easier, but if you do remember it, it certainly results in an easier differentiation. So both of these are the same. That's pretty sweet. Great. We're going to do a lot more of that in Unit 6 when we use our exponential, logarithmic, transcendental functions, trigonometric stuff in there too, to rewrite, and that'll make things easier. All right, so we've got now not a 1, not a 2, but a 3-link chain for number 3. Is my overall function a sine, a cosine, or an exponential? So what's my overall function here? Peter? Sine. So we'll start off with our sine derivative. So the derivative of the outer function, sine, goes to cosine with my inner function. and then times the derivative of my inner function. It just so happens that my inner function is itself composite. That is to say, it's not just cosine of x, it's cosine of e to the x. And so when I do the derivative of my inner function in green here, right, when I do the derivative of my inner function, I'll get to use the chain rule again, because I now need to differentiate cosine of e to the x. No problem. Is my overall, right, my overall function now a cosine or exponential? Well, it's overall cosine, so the derivative of the cosine function is opposite of sine with my inner function, in this case e to the x. And then lastly, times the derivative of my inner function. Finally, I get to do times the derivative of e to the x, which is e to the x. What? The derivative of sine is cosine with the inner, then times the derivative of the inner. The derivative of cosine is opposite of sine with the inner. Now times the derivative of the inner, the derivative of e to the x is e to the x. Let's put it all together in a rewrite and see what we have. It looks like we've got negative e to the x, sine of e to the x, cosine of cosine e to the x. What? Negative e to the x, sine of e to the x, times the cosine of e to the x. That is quite a chain. A hefty chain. That'd be like a whack-a-flocka chain. You know what I'm saying? Serious. You know what I mean? Like, you gotta, like, tick-tock with the clock amped up. You have to carry that around. Some serious backspin. All right. Let's go ahead and take a look then at, did anybody get number 3? Did anybody get, yeah, that's great news. If you're able to do ones like number 3 at this stage, then that's great. We're going into our review day. Remember, next class is our test, so you still got a little time to practice. Now comes the big bad mother daddy of them all, number 4. So we've got cosine to the 5th of theta to the 5th. Wow, and so this might be easier to visualize if we rewrite this, not differentiate, but just rewrite. If I were to rewrite this as that shorthand notation, cosine to the 5th really means cosine of angle all to the 5th. And so I'm thinking it might be helpful to rewrite this as cosine of theta to the 5th, right? And then that's all to the 5th. So if I rewrite this as cosine of theta to the 5th all to the 5th, right, then it's easier to see my overall function. Now I see that my overall function, right, is not trigonometric, but rather power. So I'll start off with my power rule. So the derivative of a power function is exponent times the base raised to 1 less. Let's do it. So exponent times the base raised to 1 less. So the derivative of x to the 5th would be 5x to the 4th. But it wasn't x for my base, it was cosine of theta to the 5th. So my inner function is cosine of theta to the 5th. So when I go to do times the derivative of my inner function, cosine differentiates to opposite of sine with the angle, and then times the derivative of the angle. My angle wasn't x though, it was theta to the 5th. So I need to use my chain rule the final time the derivative of that inner function, theta to the 5th, is 5 theta to the 4th. Put it all together, what do we have? Negative 5 times 5 is 25 theta to the 4th, sine theta to the 5th, cosine the 4th theta to the 5th. Oh gosh. Negative 25 theta to the 4th. Sine of theta to the 5th, cosine to the 4th, theta to the 5th. Did we get all the pieces? We got all the pieces? That's pretty awesome. What questions do you guys have about number 4? Okay, let's go ahead and box this. We want PDFable. And exponential function. So the derivative of an exponential function, we recognize that as an exponential because my variable x is up in the exponent, right? My variable x is up in the exponent. But unlike e to the x, which differentiates to itself, e to the x, here's the result of our activity. We found that the derivative of an exponential function with down base e is the exponential function itself, but then times some constant. That constant, right, ends up being the natural log of whatever the base is. In fact, that holds true for our derivative of e to the x. When we multiply by the natural log of the base in an exponential base e function, what is the natural log of e? The natural log of e is 1, right, is 1, so it doesn't change the value of my exponential derivative, it's just e to the x. And so it is itself times 1, right, remains itself. Let's go ahead and see what that looks like. So the natural log of the base would be ln of 5 times the exponential function itself, 5 to the x. Sometimes that's written as 5 to the x, right, 5 to the x times ln 5. ln of 5 times 5 to the x is how you wrote it before. And so raise your hand if you had number 5. That's our shortcut rule for the derivative exponential. And that does work for the derivative with respect to x of e to the x. It's just ln of e times e to the x. And the ln of e is just 1. So that rule holds true for any positive base constant exponential. 5b, what if this had been, and it wasn't on your sheet, but what if this had been 3 times 5 to the x? If I were to differentiate 3 times 5 to the x, would that be ln of 15 times 15 to the x? No way, Jose, right? Our order of operations, right, dictates that this exponent applies to the 5, and the 5 only. This 3 out front is just a constant multiplier. And so don't be fooled, right? Don't be fooled by order of operations. You would not do 3 times 5 is 15 to the x and differentiate 15 to the x. This is 3 times the derivative of 5 to the x, and that is ln of 5 times 5 to the x. And so this would just be 3 ln 5 times 5 to the x. And still a one-stepper, not a chain. How do I know this isn't a chain rule? My exponent is just plain Jane x. It's not cosine of x or e to the x, right? Or sine of x. It's just x. And so this is not a chain rule, it's just a constant multiple times a function. Great. What questions do you guys have on today's Bellwork? All right, let's go ahead and take care of our rule sheet update. And so whether you're gone last time PSATing or you were here for your activity, you want to make sure that our rule sheet is updated now. So we need to include the derivative with respect to x of e to the x, the derivative of natural log of x, and the derivative of any constant base a exponential. If you'd like to follow the same format on the back, I kept it as f of x. If f of x equals e to the x, then f prime of x equals e to the x. So if you want to spin around and add those final 3 rules on the back whiteboard, you're welcome to do that. If you'd like to stick with this notation, either way is fine. I know the derivative with respect to x of e to the x is e to the x. What's the derivative with respect to x of ln of x, natural log of x, right? What does that differentiate to? James?
1 over x.
1 over x, thank you, 1 over x. And for a non-base e exponential, call it a to the x for some positive constant a. What does that differentiate to? Ben?
ln of a times a dx.
Awesome, thank you. So we got our rule sheet and the last shortcut rules added. You're now welcome to use, right, all these shortcut rules on your Unit 3 test next class. However, I will be erasing that back whiteboard, so the back whiteboard won't be there for your reference during the test, right? Nor will you be allowed to use your rule sheet, and that's why I was encouraging you early and often to buy those neon flashcards, right? So you can be practicing with each other. A little downtime, right? A little downtime. You can pull out your little baggie of flashcards and quiz you and your friend, you and your classmate on your derivative shortcut rules. All right. Let's go ahead and make sure that your half sheet and your more chain rule practice is included with your bookwork for OTL number 9. That brings your total to a whopping 38. Give yourself credit for those you complete out of 38, please. Divide, enter, multiply by 2, and then round to the nearest half point, 32. And so even if there were several questions that you didn't complete, it could still round to 2 and get full credit on it. As I continue to include some stretchers on your OTL assignments, I don't want to shortchange your education. I want to make sure that everybody's challenged at an appropriate level. In any case, make sure you're going to have a score box nice and big. Your name, right? 1B and OTL number 9, clearly labeled. And then pásamelos, por favor. Pass from the back to the front. Front rowers, make sure they're facing the same direction. And we'll get this recorded and Infinite Canvas updated so you're ready to go going into your Unit 3 test.
Did you look at that guy? I tried doing it last night, it wasn't working out. And then you have to actually calculate that one base count. Okay, if I don't. Okay, I'll turn that in now.
Is it late absent or is it late?
Apps,
Okay, there's like absent on time.
and I think it's all 17 on that.
2019, that's okay. Yep. So then put absent on the end, and then circle it. Awesome. And then put it underneath this one. Yep. Where's the black stapler that was on Danny's before? Oh, Scott, can you pass that forward, please? Kyle, can you use this? Thanks. Yes, under it. Yes, perfect. Thank you. Thank you. Last call for number 9. Number 9. Great. Okay, ladies and gentlemen. Today you're going to have an opportunity to work with a classmate as you go through your concept and skill guide for Unit 3. Please know that I included more than you'd be expected to complete in a single test session. So as you look through, we talk about the ability to prove some of our derivative shortcut rules. Please know that you, in a testing situation, would not have to prove all those shortcut rules. You would not have to prove the derivative of the sine function. In fact, that took us most of the class period that one day. You would not have to prove the derivative of cosine. We didn't even do that one together, right? You would not have to prove the power rule. It was the back of that extra handout. Number 9, right, that included like the binomial expansion and theorem and all this stuff. So you wouldn't have to do that kind of thing. When you're thinking about those proofs that you might have to be providing, think more in terms of like our earlier OTLs when one of our worksheet addendums was proving derivatives worksheet. And you had to do things like prove the derivative of a linear function, or prove the derivative of a constant function, or prove the derivative of a constant times a function. On the end, at the end of the posted notes PDF on our Moodle website for today, review day, day 9, I wrote down kind of some possible test question proofs, you know, the ones that you might be expected to do. And so as you're looking at your Unit 3 concept and skill guide, and then there's all these proofs listed, you're not going to have to do all those on your test, right? I want to provide you with more things, right, than you'd be expected to do on your review, so that when you get to the actual test, you're like, oh, golden, I can do this. You know what I mean? And so, you know, these are more like all the things we've run into, and on your test, you wouldn't have to do all of them necessarily, because there just isn't enough time, frankly. Okay? Does that help some? Awesome. So I've included some practice. You can work on this with a classmate, and then you're going to use your smartphone or electronic device to check the answers on your practice problems on the Moodle. And these are actually on the completed notes PDF within the block. Okay, within the block. So I want you to be checking these answers as you go through. Then we're going to go ahead and do a Unit 3 stamp check. And so I want everybody to do your stamp count first before you start working with a classmate, and have that ready so that I can come around and record that while you guys are working. Guys, for our stamp check, we've got Bellwork day 1 through day 9 in Unit 3 for a total of 9 red marks, except for Scott's blue mark that I just gave mistakenly right now. We'll count that as a red mark. Then our activity stamps start at the very beginning. So I'll go ahead and pull over that graphic and show you what that looks like. Our activity stamps began back with our instantaneous versus average rate of change. And so, bless you. So I'm going to pull that over so you can look at that. And as we look at our activity stamps, those started with our average versus instantaneous rate of change activity. Okay, and so in just a minute, I'm going to go ahead and stop the recording since we've ended our discussion portion of the class, and we'll focus in on our stamp count, and we'll get you credit for your hard work.